Let's talk a little bit about the source of friction. So in this case, let's put a box on a flat surface and let's push on that box with a certain force. All right. If we think about this, what's going to happen is that box is just going to slide along. If there's no friction, it'll just accelerate and go faster and faster and faster. And if we want to think about free body diagrams, there's an mg pulling down and there's a normal force pushing up, but still that box is going to slide to the right. Now we know that friction happens when things are in contact with each other, so let's look a little bit at what's going to happen in this area. So let's look just right in this area. Let's sort of blow that area up and see what happens. So we have in that area, let's just make it really big, say what's going to happen is we've got just the surface, the bottom surface is all jaggedy, right? If you blow up and you magnify, if you looked at any sort of table, it would be jaggedy like that, and then we say, okay, there's our table going out. And if you look at that box is also going to be jaggedy, right? So you say, oh, here's the box. It's just like, oh, we'll put the box in red. It's going to be jaggedy as well, right? All right, and oh, there's our box. Okay, we'll just make it, sort of big. So we're just sort of looking at right here like a blown up section of what happens if we look in really big and it's really, really jaggedy. This jaggedness is the source of friction. All right, you can notice that if I really am trying to push this box with a certain force to the right, what's going to happen? Well, what's going to happen is this mountain is going to get hooked up in this gap, and they're going to collide. So we're going to have a bunch of bumps, and it's going to have to lift up. The whole box is going to have to be lifted up in order for it to get over the top of this mountain. And then that valley is going to fall down into here, and then we're going to have to go up again, and we're going to go up. So we're going to have to really sort of work to get over these mountains and valleys, right? And obviously, the more jagged something is, the more friction there's going to be in there. So we can see that that's the case, that friction has to do with the surface here and how that surface looks in terms of how smooth it is going to have to do with the friction. So how can we calculate friction? The other thing to think about is what friction depends on. What would happen if I put just a big, heavy something here? Something really heavy, all right? What would happen then? Well, of course, you'd see that this whole box would be heavier. It would sink farther down into these mountains and valleys, and it would be harder to slide in this direction to the right. So the heavier something is, the more the friction is going to impact it. And like we were talking before, we go back over here to our free body diagram. We're going to interact with the weight, the mg, through the normal force. So the normal force is going to give us an indication of that heaviness, and what we can do mathematically is we can say the force of friction is going to be proportional to the normal force. If there's a big normal force, if there's something really heavy up here, then we're going to have a big force of friction because these guys are going to sit down in here. And if it's really light, then it's going to be easy to bump along the top and it will be a smaller force of friction. So that force of friction in that proportionality constant is going to be the Greek letter mu. All right? So that funny letter that we just wrote is the Greek letter mu, spelled mu. It looks like a U with a big leading tail, right? So it's a Greek letter mu. That's the proportionality constant. We call that the coefficient of friction. So the force of friction is some number times the normal force. And this number is going to depend on what the material is. So if you're sliding wood past wood, right, you might have with wood mu equal to 0.4. If instead you have ice, ice is going to be a lot smoother and a lot of those gaps are going to be filled in with melted water, so there's going to be less friction. So if you slide ice past ice, you might end up with a mu equal to 0.1. Okay? Another thing that's often interesting is if you take two different materials. What if I take rubber and slide it past concrete? Well, in that case, the mu is going to be 0.7, so it's going to be a big mu. The reason this is particularly interesting is because rubber and concrete is what happens when you are driving your car around. right? Rubber tires, concrete road, you have a big mu, lots of friction, which is useful if you're actually driving your car. You don't spin out. All right, so the mu is going to depend on the material. Every material has its own mu. If you had rubber and wet concrete, it might be different than if it was dry concrete. But every material is going to have its own mu, and all you have to do is look those up in a book. You don't have to memorize those or anything. You want a mu, go look it up in a book. Somebody has the fun job of actually testing the coefficients of friction for a bunch of different materials. All right, so we have this idea of mu, this coefficient of friction. The other thing that we need to think about is whether this thing is moving or not. So you can imagine that if this red box here is moving, then as it's going up, it moves, it bounces, it comes up over the top of this mountain, and then it's going to fall back down. But because it's moving, it might not fall all the way down into this valley, but it might bounce over the top and miss that valley completely. So if it's moving, you can see that it'd probably be easier to bounce along the top and never actually go all the way down into these valleys. So moving friction, or kinetic friction, is going to be different than not moving friction or static friction. All right, so kinetic friction is going to be moving, and we're going to see that that's going to be easier. So we're going to have mu kinetic, and static friction or stationary, right, not moving, is going to be different, because if it's not moving, this thing can slide all the way down in this valley can go all the way down in this valley, and it becomes much harder to get it started moving up over the top. So we're going to have mu s, or mu static. And you can tell that since things are moving, it can bounce along the top. We'll probably be able to say that mu static is always going to be bigger, and mu kinetic is always going to be smaller for a given material. So that's sort of a rough idea of where friction comes from, and mathematically what we're going to do with it. And in our next section, what we'll do is we will actually try to solve a problem with friction and see how these come into play.